Good afternoon, good morning, and good evening to everyone. I'm Shreya Pradhan from Asia Pacific Telecommunity. It is my great pleasure to welcome you all to the Web Dialogue on overview of advances in satellite and Wi-Fi technologies in collaboration with Varsat and Meta. In this web dialogue, we will be sharing knowledge on the advances in satellite launches and terminal development technologies and its integration to new emerging Wi-Fi technologies, providing VR and AR applications and services. So now I'd like to invite Mr. Masanari Kondo, Secretary General of Asia Pacific Telecommunity, for his welcome remarks. Welcome, Mr. Kondo.
Okay, thank you, Shalia. So good morning, good afternoon, and good evening to you all. Welcome to the APT Web Dialogue. So today we organize this dialogue with Inmarsat and Meta. And I would like to express our appreciation to Inmarsat and Meta for their support and collaboration. Especially, I want to thank Mr. Bashir Patel from Inmarsat and the colleagues from Meta for joining us despite their busy schedule. So APT Web Dialogue, or AWD in short, provides a discussion platform for sharing information, exchanging views and opinions, and learning something new. So it is an intellectual agora of APT, or brown bag lunch event of APT. So AWD covers many interesting topics and fields that would stimulate your insight as policymakers, business managers, researchers, innovators, or visionaries. So today's AWD will cover issues of satellite and Wi-Fi technologies. So this is an interesting topic, and it is important to listen to and share different views and perspectives. We have 4 eminent speakers who are experts in this field, and I'm sure that their views and perspectives will shed light on our way moving forward. So again, I thank you for your participation, and I hope you enjoy today's dialogue. Thank you very much.
Thank you, Mr. Kondo. So now I'd like to invite Mr. Bashir Patel, Senior Advisor in Varsat, for his opening remarks. Welcome, Mr. Patel.
Greetings to you, Kondo-san, and greetings to Shreya and all my other colleagues who are presenting, as well as all the colleagues who are online. First and foremost, let me thank you all for joining us, and also thank APT for their hosting us, able to provide this web dialogue, basically covering the various advances that have been going on over the last several decades in terms of the satellite technology and the various applications, as well as in terms of the development that are taking place in terms of the Wi-Fi development. I go back to 20 years ago when the first router came out. And today we're looking at Wi-Fi 6E and Wi-Fi 7 development, which are really posed to take on in terms of the augmented and virtual reality kind of applications and so on. So it should be very quite interesting to hear both from Meta, who have joined us this morning or this afternoon in your case, and they will be covering, in fact, session 2 and 3 we have on the program, which talks about the emerging technology from the Wi-Fi side of things, and also the socio-economic impact in particular to the Asia Pacific region in terms of the economies of scale and the solutions that are possible with AR and VR and so on. Before session 2 and 3, both myself and my colleague, she's the Vice President for Regulatory and Market Access, Zaina, she will be covering more on the Inmarsat side of development in terms of our future networks, orchestrate, and so she will be covering that aspect in terms of what we plan to do and how we're moving forward in terms of the multi-access kind of technologies and so on. Before that, let me go through with you in terms of what are the kind of developments that have taken place. Having been involved in the satellite arena for quite some time now, over the last 20, 30 years, I go back to the very first generation of satellites that Inmarsat actually leased. I was responsible for leasing these satellites from Intelsat as well as from European Space Agency. So let me begin then with that. These are the four presenters we have, as I mentioned already, Zaina from Inmarsat and myself, and then Dr. Shahid Ismail from Meta, with Ranuka from as well from Meta as well. So four of us will be covering this session, 3 sessions this morning, and hopefully you find them useful. So without further ado, let me just move quickly on to advances in the satellite technology. So what are the real drivers behind the innovation that's been happening in the satellite technology? Well, I think if you actually look at this picture, what you see here in front of you really is a night map of the world, where the lit up areas is where obviously you have electricity. And the cost of these things are going drastically high up given current situation right now globally. But you can see how illuminated the east coast of US and Europe and various parts of Asia Pacific. When we look at Asia Pacific, Japan, Korea, Malaysia, and so on, some parts of Indonesia, eastern coast of Australia, and so on. But when you look at this, you know, what you find really is that 2/3 of the world population may well be covered by mobile technology. And of course, fiber interconnecting some of the major cities and so on. But it only covers 40% of your land mass. So we still have 60% of the global land mass where people are living there, or some one third of the world population, which in today's estimate is about 2.5 billion people without any connectivity. So this is the reality today we face. And given all the advances that have happened, both in terrestrial and other technologies, we still face this issue. So the digital divide that we see ourselves in today is still there, and it could even worsen as we advance in other technologies without the satellite system. So where does satellite fit in? Well, the drivers behind the satellite, as I say, is when you see those kind of conditions and gaps and the digital divide that we have, then you see the development that's taken place over time. I remember going back to first for 1G, it's basically an analog 450 NMT technology, and it was size of a brick, your first mobile phone, which you carried around. It's moved on ever since then. And of course, we're now getting up to 5G with the very smartphones. Basically a personal computer that you carry around with all the applications and everything else. So we have moved on, and of course it's very much IP technology driven. But those first generation analog, then we moved on to what we call GSM. In fact, it was a technical committee of the European operators that actually created a body called Group Société de Mobile, GSM, which later became Global System for Mobiles. And that 2G network was basically very much a 8 to 16 kilobit codec voice, digitalized voice. It was again digital technology that the European wanted to bring about. It was quite proprietary and gradually spread. And then from 2G, there was no data services really. It was just a voice codec with SMS applications, which then moved on to 3G with the 384 kilobit per second voice as well as data speed of 384 kilobits. And then subsequently, we now have 4G, which is much more widely spread, as we saw, but nevertheless. And then we have 5G, which is really much more focused on dense urban kind of environment with low level of latency, but much higher throughput levels and so on. So given the drive moving from one-dimensional approach where people were connected, we then moved really towards an ecosystem with global digital transformation that many countries, particularly the developed world, was trying to focus on and allow for cross-sector collaboration and so on. And what we see here is really everything being connected. Connected things, connected IoT devices, connected cars, hospitals, educational centers, and so on. So we have this transformation, digital transformation of our, if you like, our cities, urban areas, suburban areas. It hasn't so much as spread to the rural areas yet, lack of various access technologies. So because of that, I think, again, you see this growth in this particular sector of having connections in everything we possibly could. And again, this is very viable and possible with the IP kind of network that we're looking at, digital networks. Whether we're looking through fiber, different access technology, wireless technologies, whether it's IMT, as well as satellites. And of course, you can see direct to home kind of broadcasting in satellite, from the satellites, which is widespread in many parts of the world and so on. So this growth, if you like, in terms of the mobile area, which has really driven the satellite technologies to move forward as well. So satellite strategies were adapting to growing end user expectations. Mobility was very important to people, whether you happen to be mobile within a car or within an airplane or on ships and so on trains. Therefore, again, this mobile growth of the mobile devices, this proliferation of handsets, and of course, there's billions and billions of dollars being spent on miniaturization of technology, if you like, when you have a chipset, 2 or 3 chipsets which are built into a card, which then fits into a small mobile phone. And that kind of investment basically allowed us, and then the growth of data, particularly moving from 3G to 4G, that's a much larger step up increment, if you like. We went from 384 kilobit per second speed levels, then you got up to, in fact, something like 1.2 megabit, 1.28 megabit, and much higher speed levels were possible, depending upon the kind of base station technology that were being implemented and data speed. 3.8 megabit per second was the kind of speed in some of the urban areas we were seeing in the early days of 4G. So you had this proliferation of devices, you had these bandwidth hungry applications. And of course, we came back to the area where a lot of the applications and everything were on cloud, and you yourself saved all your, if you like, your data onto cloud, which you access as and when you needed it and so on. So cloud computing has been growing tremendously. And again, that is something that we also in the satellite industry is looking at in terms of having cloud computing from a satellite, from the satellite itself, which stores, because again, memory is very cheap now. And again, we'll go on to that a little bit later on, but you find that cloud computing is basically a hub, a cache which includes a lot of information, stores a lot of information. It's a storage base, basically, storage depot. And that can be quite in quite a different kind of locations. And then, of course, you have this OTT applications, which many of us all have on our handsets and phones and so on, allowing us to make calls and connect with our friends and families right across the globe. So again, these elements have driven really towards us in driving us to high-speed access to anything from any device, anywhere at any time. And this is the motivation that really, from a satellite point of view, is driving us. So these advances in technology we see in the terrestrial technology, going from copper wire to fiber optics to high capacity urban rings, terrestrial wireless from analog 2G, 3G to 4G, 5G now, and we're looking at developing of the 6G and beyond, 5G and beyond into 6G. 2030 vision is the kind of thing we're looking at now. But again, those kind of elements are important in the context of the way the Wi-Fi technology and satellite technology is also developed. So satellite, in terms of the space and ground segment technology, has evolved enormously in the last 20, 30 years. As I mentioned, when I first got involved in the satellite in the early 80s, we had a very simple bent pipe technology. First generation satellite, in terms of the satellite capacity of the first generation of Inmarsat satellites, we were looking at around 33 channels, and the cost of the terminal, cost of the service and everything else. Again, given the limitations of these satellites, You know, again, the equipment was quite expensive. The services were quite, you know, were largely used by super tankers on high seas and so on. So again, you find that the initial startup technology costs have always been high, as we saw in the context of mobile technology as well. When you had analog brick-sized phones, compare that today to your a smartphone today, which many of us carry around and so on. So again, it's that kind of comparison. You had very old at the time, that was the latest technology had available, but since then we've advanced enormously. We advanced to the extent that we have very high capacity throughputs, very advanced resilient global networks with end-to-end connectivity, integrated solutions again, and so on. So basically, we are now integrating in terms of different access technologies coming together. So what you see here is major advances. I wish I could get to this, but I can't. But anyway, major advances in satellite technologies. If we actually go through, if we take a satellite as an example first, in terms of satellite itself, you have two major elements. One is the platform itself, which is the body, the frame. The frame used to be with special aluminium alloys, which obviously were very robust, which would take the different stress levels into space and so on. And those were bulky. Although there were alloys, light aluminium alloys, but nevertheless, they still carried quite a bit of mass. And then you had the payload. The payload obviously was the computer on board the brains of the satellite, which basically did the processing and so on. Given the limitation in those days, what we had, to today what we have is we have very advanced digital beamforming processors. A lot of memory, a lot of capacity, very low power devices which are built into the satellite payload. In addition to that, you have the platform, the body, the framework. Again, we're now using carbon fiber composite materials, which is very light, very robust, very strong, hard, and so on, titanium-like structures. But it's not metal, it's carbon fiber composites. And again, that allows you to have a much lighter satellite, carry a lot more payload, if you like, in terms of functionality and capacity. And that can go airborne. And also the fact that we're moving away from carrying fuel, because fuel dictates the lifetime of the satellites. And so you don't have to carry fuel because you're going to have electric propulsion system, which are low powered, but you're taking the energy from the sun and storing it and using that in terms of propulsion system. So again, the new wave, if you like, the new generation of satellites are much more lighter, much more powerful, and I wouldn't say cheaper because you're still having fairly advanced kind of technologies, but you're able to put them into orbit with much greater level of capacity and so on. So in addition to that, of course, in those days in the 80s, we had limitation. We still had the Cold War going on between the US and in those days the Soviet Union. So what you then had really was the launches were very, very limited in terms of you either went with Proton, the Russian launcher, or you had the American, a couple of the American suppliers which gave you the launch Atlas launcher and so on. You either had those, and those were limited. And in fact, the cost per launch of a satellite of 2,000 two-ton satellite was something in the region of about $50 to $60 million per launch. And then you had to have an insurance just in case the launch failed. So again, that added on the cost of the launch to the satellite. So in those days, it was expensive, but today we now have launches. A number of suppliers of launches are there, not just US, but even private sector launches like SpaceX. We have launches from India, China, Long March, Japan. So there are a number of, if you like, suppliers of launch vehicles now, which means that it drives the cost down. So reducing the launch mass, lower class of launch vehicles to inject larger payloads and so on. The third element in terms of the advances in technology has been really very much the ground network, much higher, and of course the technology where you're tracking satellites with the antenna on the ground itself. So before we had a lot of the intelligence put on the ground stations, because obviously satellite had limitations. But today's satellite with high throughput or very high throughput levels, satellites are much more advanced. And you had in those days, again, what you had was a traditional beam, one global beam covering 1/3 of the world. Today, these satellites carry high throughput satellites, carry multiple spot beams, steerable beams. You can shape the beams over a particular country if you wanted to. So again, having these high spot beams, high-powered spot beams, and as I say, steerable beams, which you can shape as well. So again, that kind of capability, what is meant is that we, with all these different aspects in terms of the space segment, the launchers, the ground segment, and so on, this innovative use of these new technology has basically drastically reduced the cost in the satellite operator's ability to provide services. In addition to all of the advances in the different areas of these technologies, what you also find is there was also advances in the air interface design. When we came to air interface from, of course, the signal is being carried from the Earth to the satellite and back to Earth. So again, when we look at the design, and we did some very interesting development in the early 90s in terms of the air interface design, which carries the traffic, if you like, carries your voice or carries the data and so on. And again, that's advanced so much to minimize latency, but as well as to give you much more robustness in your link. The quality of the link is very important, and the ability of that link to have the data brought back to you without any errors and so on. So again, you find a lot of that innovation in the C-band, in the KU band, particularly in the L, S-band, which again, basically, and C-band as well, which are not affected by any attenuation from rain and so on. These are very special characteristics of some of these frequency bands that are used for satellite services. Same thing with L-band. L-band is used in the maritime because of its quality of the link. The link is not affected by any weather conditions that you may face, particularly in high seas when you have storms, tropical storms, or any kind of storms, or dust storms in deserts. Any kind of environmental impact is not affecting the link. That quality of the link is maintained to carry whatever the message or traffic you're actually putting forward, and so on. And again, the other bands which are affected by rain attenuation, such as KU and K, again, we have some very novel kind of development in terms of software, which allows us to keep the link, maintain the link, and make it much more robust. So it can vary in terms of speed levels, higher speed, lower speed, and so on, depending upon the level of attenuation that we might get from rain and so on. So highly cost-effective kind of links put together, given the various advances on the satellite, on the ground segment as well, and our ability to get those satellites up there in different orbits, LEO, MEO, or geostationary orbits at 36,000 kilometers above the equator. And one aspect of this is all of this is being feasible because if you look at the computing cost, that has drastically declined, and I need to update these charts, but you can find from cost from $527, we're now getting into cents, fractions of cents now. Bandwidth as well, when you look at the cost of bandwidth, that has drastically come down on satellite from $1,200 in the 90s, in year 2000, right down to today. We're actually down to a few dollars again. And when you look at the memory, the storage we talk about, when you look at readily accessed RAM on your smartphones and your computers and laptops and so on, the cost of that is getting into, again, fractions of cents now today. So storage is very cheap. Computing cost is much more lower. The bandwidth being made available as well, and we're able to reuse the bandwidth as well, multiple beams and so on, frequency reuse. That allows us to make the whole aspect much more dramatically lowering the price per megabit, if you like. So launch providers, new launchers on the market, reusable rockets are there. Again, as you can see from SpaceX, which basically launches the satellite and bring the rocket back, lands it vertically. Much cheaper launchers are there. Again, multiple satellites are being launched. Typically, SpaceX are launching 16 to 20 and more, depending on the size of the satellites, are on our typical launchers. You also have mission extension vehicles. In fact, there are refueling of satellites in orbit as well that is happening today. We're moving away from fuel-based, hydrogen-based propulsion to electric propulsion system. So again, you're taking away that excess weight, but replacing it with weight on the payload and making the payload much more powerful. And again, the future generation satellite may well have a payload which basically is a cloud in space. Cloud computing in space. A lot of storage of information is there, which readily can be made available to the ground users. We don't have to wait for that. There's no latency there, or very little latency. And then, of course, you've got the different constellation, high throughput satellites, narrow beams I mentioned already. Typically, we're now getting satellites, one satellite can provide almost 1 terabyte of capacity. And this is the reality of coming in today. Terabytes of capacity, enormous amount of capacity is available to serve through various spot beams that will be covering different countries and so on, sort of high demand areas where you have traffic and so on. Different kind of constellations, GEO, of course, 36,000 kilometers above the equator, to MEOs, LEOs, which can get down to almost 500-600 kilometers above the surface of the Earth. Very much scalable capacity and so on. We have, again, very high throughput satellites in Ka-band. Inmarsat is one of the leaders in this area. And again, you find 60 plus hot satellites covering different parts of the world. In fact, we're now getting beyond 60. It's almost about 100 plus satellites now. User terminals, again, enormous development in user terminal technology, which we'll focus on a little bit later. Patch antennas, I remember funding development of patch antennas in late 80s, particularly for aeronautical satellite communication. Which went on the side of the body of the fuselage of the aircraft. So you had six patches, 3 on one side on the port and 3 on the starboard side. And again, these patches were really developed with an electronic digital sort of switching, which tracked the signal from the satellite. So you optimized in terms of signal levels. Electronically stirred antenna, basically, they were phased array patch antennas. And the cost of those has drastically come down, which again, and these can be again used in all kinds of applications, which you'll see not just aeronautical, but trains, cars, all kinds of things. And as I mentioned already, in terms of the air interface design, developing that interface, increasing processing, the ability to have different coding and modulation as well, that came about. And really, we did a lot of trade-off when we did the design of the air interface in terms of optimizing performance and the ability to make sure through interleaving that we were able to make sure that we minimize the error rate in our air interface design and so on. So again, a lot of development in all areas of the technology really, which is, so the Ka-band, the new wave of geostationary high throughput satellites, you can see here Ka-band satellites. In terms of the coverage, these are actual beams, spot beams, which are covering different zones, if you like. So you see multiplicity of beams, different shapes and sizes, which cover different territory globally. And of course, avoiding areas where middle of the ocean and so on, like this Indian Ocean here, you see a big white area. But nevertheless, you cover the high density areas, providing high throughput, high capacity, and so on. And then, of course, you have the LEO systems, which are coming in. Those were GEOs. But again, LEO constellations, which are basically covering the globe, as you can see here. That is now coming about with other various operators like OneWeb, and you have other operators which are coming into Starlink. Many of you would have heard about, and so on. So all of these are basically constellations with moving satellites, and the ability of the ground gateway, if you like, to track these satellites and then switch between different satellites as they go past that area and so on. And again, you have to look at the trade-off in terms of that kind of technology in advance versus other technologies that are available in terms of the geostationary and MEO, medium Earth orbit satellites as well, and so on. But what it does mean is, of course, you've got lots of different applications of these kind of services happening. So there is also basically bringing together geostationary as well as low Earth orbit satellites communicating. So you have inter-satellite communication from GEO to LEO, and of course the ability of that to connect to the ground as well. So this is kind of really a step going into the next 5 years, I would say, where different operators will want to are providing multiplicity of different kind of orbital constellations, will want to actually connect them up in order to serve much more effectively in terms of the services they wish to provide and so on. And we're moving in that way. And I think you'll hear from Zaina in terms of the Inmarsat plans as well in this particular area. I've already touched upon very quickly, the technology from basically global beams to spot beam, multiple spot beam technology, which are coming out. Much improved capacity, much higher throughput levels, lower space segment cost per megabit. It really is changing the industry enormously because you're now having a beam which is concentrated power. So you have more power from the satellite to a smaller surface area, like a cell size, cellular cells, small cells, and you're able to have smaller terminals, cheaper terminals, and of course is much more cost effective. So when you look at these high throughput satellites, you really are looking at much greater throughput levels, higher performance, global coverage, much, again, in terms of connectivity, much more flexibility as well, because you're able to check, because they're beams, steerable beams you have, and spot beams, they can be steered to different areas where the demand is for the traffic. And so on. So again, that is quite important in terms of flexibility of your operations. Spot beams, wide beams, multiband, again, the capability of satellites to manage and do frequency reuse as well with multiple different kind of, as you have on a handset, which can operate basically different kind of bands that are made available for different services and so on. Very much an open architecture, easier access to satellite, very much scalable. And at the end of the day, what matters most is really the total cost of ownership, much lower cost of ownership of providing services, owning that network globally. And again, what we see here is this massive increase, given the high throughput and very high throughput satellites. We see this tremendous growth in terms of our ability, if you like, as service providers, satellite service providers, to have much more capacity, bandwidth available. So terabytes of capacity are now on geostationary as well as non-geostationary, geostationary as well as non-geostationary satellites we're getting into. So the next wave of satellites that you now see going up into space in GEO or MEO or LEO constellations really are very high throughput satellites, which will provide, again, a lot more bandwidth and capacity, and therefore serve you much more effectively with much lower cost levels, and therefore making it much more affordable. At the end of the day, what matters most is really the affordability from a user perspective and governments and so on. And so that kind of, that would be feasible given the kind of advances that we've seen now and catching up in a way really to the terrestrial technology, the mobile technology. We now caught up with the mobile technology with the technology in satellites in space segment, ground segment, and more user equipment and so on. So what you saw here, and I remember going back to the early 80s, a 32-meter dish for a satellite. Can you imagine? 32-meter across, sitting on a platform. Today, that antenna has been replaced by something you see here on the future on the right. These are the kind of size antennas that are being even used, 2 to 3 meter dishes as a gateway antenna. I think the largest I've seen now on a gateway today is about 10 to 12 meters at the most that is being used, and so on, which carries quite a bit of traffic. So technology in terms of antenna technology has moved quite enormously. When you look at the terminals as well, I remember a maritime terminal in 1982, which was really the size of a car. If you can imagine a typical car, which you then fitted on a super tanker, oil super tanker, or large cruise ships and so on. That particular size of unit has been replaced by units like this you see here. Very small, agile, gyro-based, flexible antennas, which are fitted with a dome, very robust, operates in any weather conditions, in high seas and so on. Typically vehicular antenna, patch antennas, which are fitted as well. You can see these are all kinds of vehicles and devices. And then of course you have a portable folding antenna, A3 size. You can fold it just like a book, carry it with you and so on. Built in with a Wi-Fi as well, so that you don't have to be next to the antenna, because of course you need a line of sight, and therefore you don't have to be sitting next to the antenna, because you've got a Wi-Fi built in, and you connect through the Wi-Fi, through the antenna, through the satellite, and you have asynchronous or synchronous data speeds, typically of 0.5 meg to 1 megabit synchronous speed, which is a dedicated channel that you get, and so on. So again, very much in your favor. You see a growing list of Ka-band antennas, whether you're portable for military applications, all kinds of applications really, aeronautical applications, the maritime and so on. And these are increasing really, and the cost of these typically, believe it or not, are coming down drastically as well. Development of phased array technology, again, for vehicular kind of application, business jet, handheld devices. Again, we're looking at handheld kind of phones, which I think you heard about from Apple as well, where they're looking at putting in a chipset for satellites. So the next wave of phones from Apple may well be operating with a satellite chip inside it. So the ability to work both terrestrial and satellite as well, wherever you happen to be. Moving very quickly, I'm just finalizing before I pass it on to Zaina. Again, what we see here is the advances in satellite not only hasn't really stopped, it continues as we continue also in the terrestrial field as well. Satellites can match terrestrial telco charges. User terminal costs only a few $100. Similar order of magnitude to an iPhone. In fact, iPhone is probably more expensive than a satellite terminal. Monthly fees, again, can be much more cost effective, few tens of dollars per month. Again, there are plans, just like mobile data plans, there will be plans that service providers in various countries provide. We'll move towards open architecture, all IP and 5G in a fully integrated kind of networks as well. And you'll hear more about that from Zaina. Deployment of terrestrial devices, again, growing focus on mobility, M2M services, and resilient end-to-end ground network, much higher performance, capacity, and so on. The value, I mean, the satellite operators are also evolving technically as well as commercially. They're becoming two value-added partners in countries. We have partners in countries now, where again, cost, quality, reach, and resilience is very important. All kinds of applications, whether in smart cities, multimedia, smart agriculture, aero connectivity, aero mobility is quite important, IoT and so on, connected cars. So all of these areas are very, very important. And I think the satellite operator will work with in-country partners to develop some of these kind of applications and services in order to serve the country much more cost effectively. So what is happening now? Satellite, if we look at 3GPP, they are integrating the satellite component, if you like, with the terrestrial component in order to expand in terms of coverage expansion, much higher throughput level that you would be able to get, given you have the big cell, small cell structures, 5G is small cell stadium, football stadium. But again, you might at the time need more capacity, more higher throughput. Again, a sterile beam can actually easily provide that as well, backhaul it through satellites and so on. So we're expanding, if you like, the reach of 5G to other areas of the country, whether you happen to be in dense urban environment or whether you're in isolated areas in terms of coverage expansion or capacity. If you're getting into an extreme situation of dense capacity. So combination of satellites and Wi-Fi together with terrestrial technologies coming together. So ultimate goal is when we talk about digital transformation, we're talking of transformation both from a terrestrial to satellite solution, enabling to have a much more ubiquitous, if you like, more robust 5G kind of ecosystem nationally, where we're looking at maritime mobility, aeronautical mobility, land mobility, to city, dense urban, to rural connectivity, if you like, as well as suburban and so on. Really, it's really integration of different access technologies coming together to provide a much more cost-effective solutions. Let me now pass you on to my colleague, who's going to give you examples of what Inmarsat is really doing in terms of building on the next generation of network and applications. Zeno, over to you. Thanks.
Thank you, Bashir. I appreciate it. Good afternoon, Kondo-san, my fellow panelists and APT colleagues. For today's session, I would like really to focus on the network of networks. And I think it's a good segue following Bashir's presentation. It's really exactly how we can integrate, but from the perspective of Inmarsat and how we see a truly connected future. Exactly on this one, I wanted to share this slide. I like how it looks. I like how it gives you a good overview of the spread and breadth of the satellite fleet today and how we see it beyond 2024 as well. As you may know, Inmarsat started its journey back in 1979. It was with the launch of our L-band services at the time, and it was for maritime emergency communications. Now, since then, we've moved on. The satellite portfolio itself moved from maritime to aviation, and then to land and government. And it was really to cater for the growing demands of our users. Now, in 2010, we took a leap of faith and diverted from L-band into Ka-band, really to increase the portfolio of the spectrum that we're using, but also bring about the broadband capabilities. And it was really to cater for those users that were on the move. So it's really for the mobile community. Today, we host 14 operational satellites in our fleet, with the 15th one that was launched, but it's not yet operational. And if we look into the fact that we have, I think Bashir mentioned 40% of landmass, I think we have around 50% of the world population that is still unconnected. And with that in mind, we have committed to further satellites. In fact, we have 6 new ones that will be coming up, one in Q1 of next year, which will be a dual payload, one that has the L-band and the Ka-band to cater for both narrowband and broadband capabilities. But we will also be targeting the pole with 2 payloads in the HEO orbit. And this is with our GX10. And then we will follow with 3 more satellites in our Ka-band Global Express constellation for our GX789. Next slide, please. Bashir. Thank you. But this again is not yet the network of networks, because as you see here, we have the L-band, which is our ELERA narrowband, and then you have the Global Express, again, Ka, and then the S-band, which is our European aviation network. Now, with all of this is not really what the customers needed. And with that in mind, back in July in 2021, we have announced Orchestra. Orchestra is our game-changing network that was intended to cover the needs of our customers, wherever they are, however they need them and whenever they need them. If I can take you to the next slide, please. Thank you, Bashir. So what is Orchestra? And for me to illustrate this, I wanted to share with you a small example. In fact, it was a story back in 2011, I think. I was flying from one country here in the region to back home. So I live in Abu Dhabi. And halfway through the trip, mid-air, we were told that the aircraft will be diverted to another airport for security reasons. And at that point, it was utter chaos in the aircraft. I mean, there were colleagues, but everyone was panicking. And it turned out to be a bit of a, I don't want to call it disaster, but it took us a good few hours to know what the situation was. We were 30,000 feet mid-air, no possibility of communicating, talking to anyone. You don't know what is happening. And there is no possibility even to check what the news, what the security issue could be. And of course, the captain and the crew would not say anything. Now, today we go on planes and it offers Wi-Fi connectivity. And in this instance, to be honest, we don't ask who the provider is. We just get connected. We don't ask what frequency this is on. Again, we're just being connected and what the technology behind it is. What we are after as users, as citizens, as consumers, is just connectivity. And this is exactly what Orchestra is. So for us, Orchestra is really to provide that end user, that consumer, with connectivity as and when they want it. Again, for them to worry about which technology, which frequency they are using, they will not do that. This is our job, and this is where we will orchestrate it in the best way possible for us to provide it to them. Now, with our L-band, ELERA network, which is providing the resilience that the consumers will be after, Global Express for our broadband capabilities, what was really missing was the terrestrial 5G element, which again will be needed in high demand areas, but also the LEO network, which again will be able to provide this low latency gap as such, but it's really targeted to particular locations. If I can move to the next slide, please, Bashir. Yeah, thank you. And this is really, it's a layer of networks. This is how we, as in Varsat, we will be orchestrating which network to use at which point in time, with the overall objective and aim of serving the end user, the customer, again, being our overall objective. So to be looking at it this way, you will see that there are different networks that provide different capabilities. And it will be, again, up to us to decide which one to provide and when, with the end user benefiting from it all. Because not all consumers, not all customers will want low latency. This is not, if you're in the middle of the ocean, and you want to send a safety message, you don't need LEO for that purpose. L-band will be your go-to solution. If you are wanting to streamline videos, it's a different story. And this is where broadband capabilities will be needed. If you are doing a live session like we are today, then yes, you need low latency. But that again will be targeted for those locations and those use cases that are unique. And if, again, you want to be in hotspot areas next to shores, next to airports, then again, you're looking potentially at a terrestrial solution. Now, with all of this mix, again, it's really where we do not want to be all things to all people. It's really about just making sure that we are delivering the best for our customers. Thank you, Bashir. Please, next one. So I'll be just going through, and I'm mindful of the time. I'll not take too long, but just to go through some of the applications that we are providing in this future network of networks within Orchestra that, again, has all of the different layers within it. We have the smart passenger cruise ships that are powered by low latency connectivity solutions, and then extending Inmarsat services for the first time, in fact, to small coastal vessels and offshore energy platforms, and as well as remote operations for a smarter maritime vessels. Now, for the large-scale IoT, again, our go-to solution will be through our L-band network, but that will allow customers to connect, manage, and monitor their networks on the cloud. With the airplanes, we are looking at a number of smart operations, whether it is in fact to monitor the aircraft health, the cabin environment, or the crew applications. Next one, please, Bashir. Yeah, thank you. And then we look at urban air mobility, which is again something that will be needed. We've seen it even in pandemic times, to be honest, where we just wanted to use these UAVs pretty much to drop parcels or to track some of the activities as well around. But this is really growing with complete command and control for a safe operation as well. Again, could be using the L-band in this case, our LRA network. Now, when it comes to tactical private networks and in a defense world, you will need to be able to have access to remote aid, forces and emergency teams for them to connect and send data back home. And it's quite important for that particular purpose. All of this is, and I think, Bashir, you've touched a lot on it, on the cloud-based application, which in our case can be used for electronic bag, flight bags, for example, for aviation services. If maybe we can go to the next one, please. I want to move into so this is just a general overview of, again, examples of LRA on the L-band system. You will see here it's mostly on the narrowband satellite, but again, smart agriculture, for food purposes, smart cities, all of this is really using our LRA network in an orchestra environment. Next one, please, Bashir. Thank you. So with all of these advances in technology and developments, in fact, it's great to have all of these ideas and the technologies being there, but if you don't have the backbone, which is the spectrum, for you today and in the future, for you to be able to cater for the continuous increase in users and their demands, then we will not be able to deliver. And I wanted to touch in particular on our main bands for today. I'll go through them quickly. So for our C-band, it's really one that is using our, we use it for our gateways and our traditional gateways, the ones that carry the safety traffic and L-band operations in general. And these operate in the 3.4 to 3.7 giga for in the C-band and the 6.425 and 6.725 in the uplink. Now, any potential interruption or interference into these C-band operations will be impacting our satellites, which will then be impacting our operations beyond just the area of the gateway, in fact, within the footprint of the satellite altogether. Now, in the next one, please, Bashir. Thank you. Now, the main legacy band, as I've mentioned, like the LRA, is our L-band, and it has been the case for so many years. As you saw, you will find that it's heavily used for all mission-critical applications, whether it's at sea, in the air, or on land. In fact, on most long-haul aircraft, you will find the Varsat systems using the L-band, I think around 90% of them. Our legacy GMDSS, so disaster relief, for the maritime is also found heavily on all big tonnage vessels, but they are also using our L-band, in addition to all new applications, as I've mentioned, the agriculture, the mining, the urban air mobility, and the smart cities that will be relying on the L-band. Now, with the onset of IMT in adjacent bands, they will be going below the 15-18 megahertz. There is increased risk of interference into these operations. And we've been working with regulators globally, to be honest, to seek sufficient guard band and protection in order to allow both technologies to coexist and strive. Thank you, Bashir. Next one, please. And if I can take you to the KA band in particular, as you saw from Bashir's summary and presentation, there is a huge emphasis from the satellite industry in general on KA band, it being the remaining KA band for satellite that is available. This is really our growth band, not just for Inmarsat, but again, for the satellite industry. And you saw we are expecting within the 6 new satellites, they will be relying on Ka band. Now, users are demanding connectivity on the move, and they want broadband connectivity for that purpose. And this can only be done through Ka on a global basis. We've started this exercise back in 2015 when we took the upper 500 megahertz, so 29.5 to 30 megahertz, gigahertz. We've taken the 500 megahertz for Ka band for what we call eSIM, but this is exactly what Global Express is. And then back in 2019, because again of increased demand on broadband connectivity, we have gone back with additional requests for spectrum as well. And WRC-19 was successful in us reaching an agreement, in fact, that would give the extra 2 gigahertz of spectrum, and it gave it in a fair way and treatment by keeping this band to satellite services with the current incumbents, so the fixed and the mobile services, while giving the IMT industry the adjacent 26 gigahertz band. So again, we would like to request that regulators keep to this arrangement to allow the 2 technologies to grow, to coexist, and to strive together. And the next one, please, Bashir. Thank you. Now, we talked about the future of networks, the network of networks, the applications involved. We talked about the spectrum that is needed for all of these applications to coexist. But in this penultimate slide, I'd like to touch really on some of the best practices surrounding the regulatory regimes. Because without these, it's really very difficult for the services to be introduced. And if introduced, they cannot be sustained for long periods of time. On the licensing side, it is really important that the licensing regimes are not prohibitive. For example, when you talk globally, and satellites are by their very nature global, and if not regional at least, we do need to remove those barriers to entry. And with that, for example, local incorporation, individual terminal by terminal licensing, and then the movement of terminals between countries, if we facilitate it through free circulation or blanket licensing, it really makes the introduction, the promotion, and the growth of these services quite possible at the very least. And it is really important for regulators to look at this, not applying generic licensing rules to all types of services. Again, because the satellite services are different, they are unique, and they target quite niche markets, and they are global. It is very difficult to impose domestic licensing rules that are targeted for a different user base as such. And it's really important for us, again, if we're looking at closing the digital divide, and we need to embrace all these technologies in the longer term to serve our communities, we need to be fair, transparent, and supportive of all technologies, maybe in a technology neutral arrangement, promoting competition, whilst removing the domestic constraints, as I've mentioned, including, in fact, the security concerns, because these are now addressed in a more advanced way that could cater for all the different national needs. And all of this should be done taking into consideration all potential stakeholders. I'll stop here, but happy to take any questions afterwards. Thank you.
Sharia, I think we probably move on with, and I'll take the questions for everybody at the end. Would that be better?
Yes, Mr. Bashir.
Okay, so why don't I stop sharing and I'll pass on to Renuka from Meta to start her session 2 presentations. Thank you.
Thanks, Bashir. Thanks, Zaina. Let me just share my presentation. Please let me know if you can see my screen.
Yes, Ms. Renuka, we can see your screen.
Thank you. Hi, everyone. Good afternoon. Thank you, APT, for having us here today. And thanks, everyone, for joining us today. Some of you may have already seen what we are going to present, and this may be new to some of you. So please feel free to ask questions. I have a couple of my colleagues here today also joining us. Just to quickly introduce, I'm Renuka Rajaratnam. I'm from Meta. And Meta has been working together with a group of companies that are interested in Wi-Fi technologies. These companies range from technology vendors to technology companies such as Apple, Broadcom, Cisco, Google, Hewlett-Packard Enterprise, Intel, Microsoft, and Qualcomm. We've been working together for the past 5 years to encourage and support governments in opening up more spectrum for Wi-Fi usage, as we see that this is a critical gap in the connectivity globally. And yeah, so today I'm really here to provide you a background, one-on-one on the global developments in Wi-Fi technologies. And I also have colleagues on the call from HPE and Apple and Intel, I saw. So if we have time, we are happy to answer any questions you may have also. So jumping right in, I would like to first touch on what are the key internet growth and trends. So Cisco has released this networking index report. It does this annually. And in the report, they have found that most of the traffic that goes through in APAC is through local access technology. In their latest 2021 update, they found that fixed access and Wi-Fi networks represented 52.6% of the world's total internet traffic. And if you can look in this chart itself, majority of the traffic over 2017, 2018, 2019 have been over fixed Wi-Fi networks. And the forecast from Cisco was that this was going to inevitably grow even further into to cover almost about 50 to 60% of total traffic by 2022 and 2023. Wi-Fi has also been important and will continue to be important for 5G technology. Today, Wi-Fi supports a majority, over 50% of mobile data traffic. And again, Cisco predicts that this will grow to about 70% with the new 5G networks that are going to come about. So this really emphasizes how important Wi-Fi has been in terms of our internet usage and what we have been doing. And I don't have to emphasize this, but I think all of us can agree that it has been vital during the pandemic, especially as people moved to work and study and pay bills and do basic things, everyday things online, shop online, and everybody was living online. We saw how important it was to have a consistent and sustained Wi-Fi connection at home, and for our kids to study, for us to be able to do work, for us to be able to go to see a doctor without having to take a PCR test. These were all very important applications that grew and became more important for us during the pandemic. And now Zoom is used as a word to say, do you want to get on a meeting? And that's how life has changed for us. And Wi-Fi has really enabled that change and evolution. And for us to continue moving in this direction, the other thing that we are seeing now is more companies are hiring remote workers. They don't feel the necessity to hire within their countries. They can hire across borders because people can work from home. They've realized that people can be productive working from home. In addition, there are a lot of new industries that have grown, or applications that have grown, like telemedicine and other sorts of facilities that we would usually have to walk out and go to a store or building, for instance, to top up our card. We can do it with a click of a button online through our laptops, our phones, in the comfort of our home. And all this is usually done with a Wi-Fi connection. And this will continue to be the case. And we expect that Wi-Fi will become integral in the way people connect with the internet. And especially as Meta and also for the group of companies, while we do feel that as users should have the best type of connectivity available for them. And that is why today we're here to speak to you about why Wi-Fi technology is an important consideration for regulators in the region also. So I'm going to talk a bit more about the spectrum needs for Wi-Fi. Currently, Wi-Fi uses the 2.4 and 5 gigahertz bands. If you were to look at the first two rows, you can see that over the past 2 decades, the last time we were given a Wi-Fi allocation was in 2003. So over the past 2 decades, Wi-Fi has shared 2.4 and 5 with Bluetooth, with baby monitors, with all other sorts of applications that are typically class licensed or under general use license or under license exempt. We've shared with them this 500 megahertz plus or minus spectrum. And this has meant that it has not been very sustainable in terms of how we want to grow. While we have managed to stay efficient, if we are looking into the future, especially for a company like Meta, where we call it the metaverse, others may call it Industry 5.0 or digital transformation stage 2, you know, we do see the need to have better Wi-Fi connectivity that can handle the high bandwidth applications, but also that can handle the very high device density environments we are going to see, not just at home, but also at work. We are going to see, we expect to see that right now, for example, in countries like Korea and Japan, the device to person ratio is almost 5:1 or 10:1. Even for me at home, I would consider myself a low tech person. I think I have about 6 to 7 connected devices. I have my smart TV, I have my handphones, my laptops, my tablets between me and my family. And that's only going to grow as we move more online and we move into more smarter homes. We have more connected devices in our homes and more connected technologies, both in our homes and in the office. And this also means that there's going to be a very device-dense environment. And for that, we would need more spectrum to provide Wi-Fi the room to grow. So 6 years ago, the companies that I just showed, we identified 6 gigahertz as the new greenfield band that would really help us. And we have worked together to develop the right standards and the right protocols so that because of that, today we're able to launch several devices on the market. And I'll talk about that a bit later, but I just wanted to quickly touch on just visually, if you're looking at this slide, you can see that 6 gigahertz doubles the amount of spectrum that was available for Wi-Fi 20 years ago. And this spectrum is really intended for the growth and evolution of Wi-Fi over the next 20, 30 years, as we move into a different stage of the internet, as we move into a different way of interacting with online technologies and applications. So I think this is what is important. And particularly because of the wide channel, because of the wide frequency range, we are able to access 760 megahertz channels and 14 80 megahertz channels. And with the next standards that are being developed by the IEEE, we would also be able to access 320 megahertz channels. The whole point of having these wide channels is firstly throughput, of course, with your high data rate applications, if you're talking about immersive applications. For example, a virtual reality, if you're using virtual reality or mixed reality to do, for instance, quality control in a factory. If you're based in Asia and you're in Singapore, for instance, and you're doing quality control for your factories in Taiwan, then that kind of application and that kind of usage will require high download and upload data speeds. And for that, we find that the optimal bandwidths are 160 megahertz channels. And also if multiple people are doing it, for example, if in the Singapore office, there's a team of 6 or 7 people doing the quality control together for a factory in Taiwan or for multiple factories globally, you would need to have the flexibility to move from channel to channel, so to prevent co-channel interference and also adjacent channel interference, which could degrade the performance of how mixed reality applications or any virtual reality applications are rendered. Ideally, the 320 megahertz channels will also provide the ultra low latency that we see is the trend for the future applications of the internet, in addition to the 160 megahertz channels. And this is currently under development also as Wi-Fi 7 with the IEEE. The standard is called 802.11be. So just moving on to the band itself, the characteristics of the band. So I've gone through why the band is an ideal band for Wi-Fi technologies that are the next stage of evolution for Wi-Fi applications because of the large bandwidth and the multiple large channels that we get. But also, and as mentioned by Inmarsat earlier, we are able to work together with satellite and other incumbent services in the band to deliver the connectivity that users want. For instance, in the US itself, these are the typical, the US which released the full band for Wi-Fi 6E connection. These are the typical applications that were in the band: fixed services, utilities, public services, safety and TV pickup. Broadcasters were also another important incumbent. And all of them together, our companies worked with them to ensure that we can put in place the right technical parameters and the power limits to make sure that we can coexist and we can transmit in the same band as them under a non-interference basis. And we believe this is also the case for a lot of countries in this region where you have fixed services or fixed satellite services and public emergency services. And we don't think it will be an issue to deploy Wi-Fi in the same band today with the equipment and the standards that are already out. So just a brief on the standards that really allow this. So we have moved on to 11AX now, which allows, and 11AX is really created in mind with the high device or multiple user environment in mind. It really allows for multiple devices to be on the same channel, multiple users to be on the same channel, and it does not degrade the Wi-Fi performance at all. So 11AX works on 2.45 and 6. In 6, this is called Wi-Fi 6E, and this is what will be important for the next stage of the internet application evolution. 11B is currently being worked on and it's under consideration. And this will really allow for 320 megahertz channels to be used eventually. And both of these see peak data rates of up to 10 to 12 or 30 gigabits per second. I'm currently at this Dynamic Spectrum Alliance Summit here in Paris, and our colleagues from Broadcom were testing out their Broadcom Wi-Fi 7 gear under a trial license here, and it was showing 4 gigabits per second speed both ways for some of the applications they were testing out today. So it's quite impressive. And on Wi-Fi 6E, we were able to show up to 1.7 gigabits per second download data rates also. So it really will enable applications that require this kind of speeds, especially if you're talking about enterprise office environments, and also if you're talking about handover from 5G to Wi-Fi, if you're talking about very dense device environments, also like museums, sports stadiums, and so on and so forth. So these are the standards that will really set the foundation for these, the innovation to develop. And because of these standards that was set very early on and they were out, I'm not going to, okay, I'll quickly go through this slide. So just in terms of certifications and the products. So Wi-Fi 6 came out in 2019, and the Wi-Fi Alliance also now does Wi-Fi 6E certification as of Jan 2021. More than 2,000 Wi-Fi 6 and 55 Wi-Fi 6E certifications have been given out. In terms of the FCC and also the Korean regulators, there are several countries that are now proceeding with their own national level certifications. We also have more than 200 products targeting various form factors and use cases already being introduced. So the standards ecosystem, the technical ecosystem is already ripe and was already ripe for Wi-Fi 6E and Wi-Fi 6 devices. So Wi-Fi 6 devices have already been on the market for a few years, and Wi-Fi 6E devices have just started entering the market. Just to show you a list of what devices are available in terms of your PCs and what are kind of your standard workhorse devices. You can see the whole list. I'm not going to go through these. I've highlighted Razer because this is actually a Singaporean-owned brand. So it's actually a local brand. And obviously Samsung is a Korean brand. So you can really see that local Asian companies are really taking advantage of the growth in the technologies and the evolution of these technologies to actually start selling new gaming laptops and selling new generation of equipment that are meant for these applications. I also wanted to highlight the list of Wi-Fi 6E products that are now on the market in terms of access points and smartphones. I think if you were to, today Samsung, Apple, I believe Apple also releases, and Google also have released their phones that are Wi-Fi 6E compatible. We also have several routers already on the market and which are deployed in countries where the band is open. And very importantly, I wanted to bring attention to the fact that Comcast and Verizon are also fixed service providers who have created their own access points based on Wi-Fi 6E technologies. So really this provides adoption of this technology in your country will provide your local players in your local industry to really innovate and also build on this. So it's not just a play by the major companies out there. So that's an overview of where we are, what the spectrum we need is, and where the ecosystem is and how the device market is ready. And I just wanted to go down to some of the use cases or device categories that we would usually be looking at when we talk about Wi-Fi 6E. So the first one is quite straightforward. It's low power indoor. This is just you using Wi-Fi in your home or office. 6 gigahertz is expected to deliver up to 1.4 gigabits per second, as I mentioned earlier. 1.7 if you have a very clean channel at a 7-meter distance, even with obstructions. And this use case is really when you're at home, obviously you have a router or multiple dwelling units, high density enterprise networks. So if you have a lot of people with a lot of devices within one room or area, indoor public venues, stadiums, and other sports venues, for instance, galleries, art venues that use AR, VR to showcase the art, there it'll be very helpful in industrial IoT. Very low power is the next category, and some of it can also be seen as client to client. What this means is, for instance, Meta has developed the Ray-Ban Stories, which are these smart glasses we did in collaboration with the Luxottica brand. So they're really glasses like these, and obviously they're sunglasses, but they connect to your smartphone, and the connection from here to here is through Wi-Fi. So our current generation of glasses are connected through Wi-Fi, but the next generation are expected to be connected through Wi-Fi 6E. And obviously we're not the only ones developing glasses or wearables that will be tethered to another client or to your phone, for instance. And that client-to-client connection will be close, and it will be at extremely low power. And that's why we call it a very low power category or device. So currently the EU, UK, and South Korea allow up to 14 dBm EIRP, which is far below any level that might lead to any harmful interference to existing services or incumbents, for example, broadcasters in the band of fixed services. So VLP is really targeted for mobile usage. So it's on-the-go usage where you have a mobile connection to your phone, and the phone is then tethered to your glasses or your watch or anything else via Wi-Fi 6E. So the last category I want to touch on is the standard power category, and this really allows for up to 20 gigabits per second outdoor coverage. This is also an outdoor play, and it's really meant for like point to multi-point rural connectivity use cases, and for places where it's probably you wouldn't see other kinds of networks there. These are good alternative to as a fixed wireless access service, and it can deliver low latency Wi-Fi calls and next generation experiences such as AR and VR also in rural environments and remote or underserved environments. Yeah, so that brings me to the end of my presentation. I know it was quite quick, but I wanted to give a quick overview of what the Wi-Fi trends are, the new technologies are, what we're using them for, and how you can think about them in terms of the device classes. I will look forward to your questions, but for now, I'll pass over to Ismail, who will take you through the second portion of Meta's presentation. Thank you.
Thank you very much, Ranuka. Can everyone see my screen?
Yes, Dr. Ismail.
Okay, thank you so much. So firstly, I'd like to thank APT and Kondosan and my fellow panelists and Bashir and Zenia, and also the other colleagues from APT, Shreya, who has been very helpful in organizing this APT Web Dialogue. So just to introduce myself, my name is Ismail Shah. I have recently joined Meta about 3 months ago. And I believe most of you would know me from my past experiences that I had in the region. So I'm very pleased to be here at this APT Web Dialogue. So you heard about the technical aspects of the satellite technologies and also the Wi-Fi technology. I would mainly focus on the socio-economic benefit and my benefits, and my presentation is not very long. I'll be referring back to the Wi-Fi presentation and the satellite presentation that were presented earlier. So looking at the socio-economic benefits first, all of you are aware that due to the pandemic, all the activities have moved online, and the primary interface had been Wi-Fi, whether these are health-related connectivity or education or work. Most of them have been using Wi-Fi. And as we move into the future, this hybrid mode or this remote connectivity, remote working will increase, and we can only see an increase in the use of Wi-Fi. The Wi-Fi, along with the satellite technologies that were presented earlier, this can provide a very low cost and high-speed broadband, provided you do have the last mile, which is the Wi-Fi, to be high-speed to the underserved areas, and that will rely on the satellite connectivity at the back end. And that is aligned with the national plans that many of the countries have, and this was also highlighted by Bashir, where he mentioned the satellite coverage, and this can be really helpful in conjunction. So Wi-Fi in conjunction with the satellite technologies, and you saw the many different usages of Wi-Fi, both in low power and outdoors, and also the indoor usage. So that's one aspect of it. You also saw the different ways that Wi-Fi has been used for video conferencing and all the other activities. In terms of numbers, the additional traffic that was generated during COVID time, that was about 5 exabytes. And according to one of the studies done in Australia, the high data demand rate during peak hours in Australia was 12.4 terabytes per second. So the traffic demand has increased, and that also has to be provided by, and one of the main technology to provide that is, of course, Wi-Fi. And the existing technology, the way it is not going to be sufficient for the future applications. So we need more bandwidth, we need higher speeds. The other benefit that the Renuka in her presentation alluded to was that if this 6 gigahertz spectrum is allocated to Wi-Fi, and the same fact was also Zinnia also mentioned, then in that case, the expense that has already been made on the existing fixed wireless network and satellite network, and the users of those technologies, they can continue to use that. So no new investment would be required. So that's one economic benefit that we will have. Secondly, if we do need to, let's say, if we want to allocate it for something else, then those incumbent users have to be allocated some other spectrum. They have to be moved to the new spectrum. So that will also not only result in delays, but there is a cost associated with that also. So in this case, if it is used for Wi-Fi, all these costs and are not there, and you have the benefit of the continued availability of the existing technologies, and that also is complemented by Wi-Fi. There is, as was mentioned, you saw the whole list of laptops and the access points using that have been developed. Like you saw the numbers, 320 million to be shipped in this year, the Wi-Fi 6E devices. So they are already here, and they can immediately provide the data rates that are there to be supported. And in fact, the deployment in some countries has already started. For example, in Canada, you can do a search and you can find out that Rogers actually has deployed Wi-Fi 6E to provide broadband connectivity to their home users. The other misconception that I would like to remove is that the Wi-Fi 6E or Wi-Fi in the 6 gigahertz is actually not in competition with 5G. Both these technologies actually will work hand to hand. And you saw in the preceding presentation, that the Wi-Fi offload increases as we move into the newer technologies. So about 7% of the Wi-Fi, of the 5G data, you saw that will be moved to Wi-Fi. So this is not a question whether we need to have Wi-Fi or IMT or 5G. IMT is the name that ITU uses for 3G, 4G, 5G and beyond technologies, international mobile telephony. So both are actually required. And there is enough spectrum for IMT that has already been identified in WRC 19. To be more precise, it has the spectrum that was made available is identified is 17.25 gigahertz, out of which 14.75 gigahertz has already been harmonized worldwide. That means that across all the 3 regions of ITU, this is the same spectrum that has been identified for IMT, 5G, and 6G technologies. And as I mentioned earlier, so if you have all this traffic on Wi-Fi and there is no opportunity to offload to Wi-Fi, or the opportunity to Wi-Fi is limited because you do not have enough spectrum for Wi-Fi and hence it cannot take the load, what will happen? Your 5G networks will become more expensive because you cannot offload the data to Wi-Fi. They will be less efficient, and that means that the investments of the mobile operators will also increase, because then they need to have a much denser 5G network, and more that will consist of more small cells, especially in the dense urban areas. So as we move into the 5G, the requirement for more bandwidth to offload the data transfer, that means to Wi-Fi 6E and then eventually 7, will increase. And with 5G, as we may have more 5G deployment, so will the requirement for the unlicensed spectrum. And the only choice we have at this particular point in time is the 6 gigahertz of spectrum. The spectrum in the 6 gigahertz band, the actual spectrum is 1.2 megahertz. So that's the second aspect. So first you saw the social aspect, that the current services will continue. Secondly, it's the 5G component of it. And thirdly, if you look at, and the third one is actually the innovation, and that can happen if this allocation is made. So in order for this for you to understand this, the new internet that we believe, we call it metaverse, and as Ranuka mentioned in Web 3.0 or Industrial Revolution 5 and all the different names. So if you go back to 1995 and look at the internet that we had at that time, how many people could have imagined that the internet will evolve into something that we have now? So similarly, we can, who can imagine? I mean, there are people who have some idea about this, how the evolution would look like, but definitely augmented reality, virtual reality is going to be part of all this revolution. So the way internet will change into the future, there is an associated economic development with it. So for example, you see with the current development in the internet, you saw the digitization process, digital governance, digital economy, and all these things that you see that the countries are actually, they have a roadmap and they are using and they are talking, and some countries have implemented the digital roadmap that they have, and other countries are still on the road. So we need to be prepared for the new wave of internet that will definitely have AR and VR as one of its main components. So we now have these opportunities, or the countries now have this opportunity in terms of software development, in terms of targeting new sectors that right now we cannot even think of. For example, the infrastructure, the buildings, the city planning, and all that you can do with VR. So right now, if we do not embark on this roadmap, imagine the technological, social, and economic lag that the country would suffer from, and the citizen would suffer from if they are not part of this revolution. And we believe at Meta, and then we have also research to prove that we need to have this Wi-Fi 6E, which is actually full band for Wi-Fi. Otherwise, the full advantage of this new development, new web that we are moving into, that we will not be able to achieve that fully without this. You saw some of these numbers before, but just to put things in perspective, if you go back to the Wi-Fi itself, this is the economic contribution of Wi-Fi so far, 3.3 plus trillion. The number of devices, these are the current devices that is happening, 4.4 billion. The 6E access points. So this is the access point that you use to install in your home, and then the devices itself are 350 million. So you can see all these numbers, and you can see that the devices that are in use and the different numbers that are there, all pointing out towards one thing, that Wi-Fi usage is on the increase, and every device that you can think of that connects to the internet somehow has support for Wi-Fi, and eventually it will have support for Wi-Fi 6E and then 7 also. And the economic benefit in terms of the dollar value currently is estimated at, as I mentioned, 3.3 trillion. That is going to grow to 4.9 trillion by 2025. And you can see the breakup on the right side as far as the different countries are concerned. So the numbers are there to support the technologies that needs this Wi-Fi 6E that is being developed. And I hope that none of the countries would lag in this area, and they will do this allocation. So just to conclude, a few takeaways. There are socio-economic benefits for the allocation of full band, which is 1.2 gigahertz in the 6 gigahertz band for Wi-Fi. And it's in many different ways. As I mentioned, the incumbent can continue to offer their services. No hardware replacement is required. Wi-Fi, as I mentioned, is the enabler for the new evolution of the internet, which we know it by the name of metaverse, and there are other names for it too. And metaverse, by the way, is not just like Meta or Facebook's product or platform that it is working on. There are many other countries that are working on. In terms of the economic benefits, it will complement 5G, especially in terms of offloading the traffic to Wi-Fi. You saw that all the laptops and smartphones that are there, they are supporting Wi-Fi, and they'll continue to move on into Wi-Fi 6E and 7. Economic development in terms of the local apps and the use cases and the digitization or digital economy contribution towards that, the efficiencies that you can introduce. This also will have economic benefits. And as we move into the future, one of the most important part would be the new applications that are being developed, like we were in the 90s. Those countries who had mature internet and they were on the right path. You saw that many platforms were developed using the internet, like Facebook, Google, and others. And similarly, you also saw the application development and software development. And here now we have another opportunity, and I hope that we take advantage of that. Thank you very much. So if there are any questions, we of course can answer. All of us are here, yes.
Thank you, Dr. Ismail, and all our speakers for sharing your informative presentations today. Before moving on to Q&A session, may I request all the speakers to open the video for a group photo session? Yeah, my colleague will help us take the photo screenshot, so keep smiling. Okay, 1, 2, 3, smile. One more. 1, 2, 3, smile. Okay, great. Thank you. So I think all of the questions have been answered by my team. Is there any more questions from the audience? Okay, so now we've come to the end of this web dialogue, and we would like to express our sincere appreciation to the distinguished speakers from Varsat and Meta for sharing their knowledge today. And thank you everyone for your active participation. Please do provide your feedback through the server link that will be shared in the chat box. Also, for the presentations today, we will it'll be available at our website very soon. I would also like to invite you all to join us for tomorrow's web dialogue, which is on unsolicited commercial messages on current policy, regulation trends, and future collaboration in the Asia-Pacific region. That will start tomorrow, 1:30 p.m. Bangkok time. So the details of this dialogue is also provided in the chat box. Once again, thank you everyone for joining us today, and see you at our next web dialogue. Thank you everyone. Thank you.
Thank you.
Thank you all very much.
Thank you.
Thank you.
Thanks.
Thanks.
Bye-bye.
Bye-bye.
Bye. Bye, everybody.
Bye-bye.